Okay, as we've seen then, a vector v2 equal to 1, 1/2, and a vector v1 equal to 1, -3. These aren't drawn to scale, but they would be in these two directions. Will have the characteristic that when transformed, v1 is going to become 5 times as long. It's going to be multiplied by -5. It'll become 5 times as long, but it'll also reverse direction. So the transformed vector here is going to be back here, and it's going to be 5 times this long, along the same line though. v2 is going to multiply by its eigenvalue 2, so v2 would just become twice as long and maintain the same orientation, same direction on its line of definition. Okay. Now I was going to draw that, and I couldn't because I didn't have enough board space. Kind of filled up the board space that I might have used to do that. I'm going to draw it anyway. I'm going to draw it very small. Let me get my colors here. Okay. Well, I guess I've kind of... No. Okay. Okay, so real small down here. I've got my v2, which is some vector whose y component is twice as big as the x component, according to what we've done here. And I've got v1, some vector whose y component is -3 times its x component. Not sure I quite got that direction right. Okay, now this is going to transform over here in such a way that my v2 vector, I think I called this v1, called this v2, this is v2, this is v1. My v2 is going to become twice as long and maintain the same direction. So let's see. Okay, that's in about the same direction this is, and it's twice as long. Okay, this is going to become 5 times as long. Since the eigenvalue is negative, it's going to map in the opposite direction. So you're going to have something like this. So this purple vector goes to here, this vector goes to here. We can see that this vector will have the effect of increasing areas. And it will have the effect that any vector along this line maps along this line, any vector along this line maps along this line, but reverses its direction. The orientation of any figure that we get when we transform according to this rule is going to change. If we go from the v1 to the v2 vector, it's counterclockwise here. From v1 to the v2 vector is clockwise here. All those things are relevant. We also see that areas are going to increase. Okay, and if we do the determinant of this matrix, we see that the determinant is -4 and -6, which is -10. Okay, now this vector getting twice as long and this vector getting 5 times as long makes it plausible, at least, that this parallelogram here, it's actually more than plausible, so I mean it's very clear that it's the case, that this parallelogram transforms to this parallelogram, and this one has twice the dimensions this way and 5 times the dimensions this way. It's going to have 5 times 2, 10 times the area. So this transformation increases area by a factor of 10. You can see that in the way the eigenvectors behave, but you can also see it in the way the determinant behaves, and reverses clockwise with counterclockwise.